Questions, questions, questions. Big questions like, how do things work? And, even more importantly, how do we find out how things work? Let's take a closer look. In antiquity, people thought we could just think really hard and use our common sense reasoning abilities to figure stuff out. And that's not generally a bad idea, but it turns out that almost anything that the ancient Greeks believed about physics or chemistry or biology was completely wrong. The problem is not that the ancient Greeks were stupid, far from it. It's that the universe is just more complicated than we think. And it's probably even weirder than we can imagine. Just thinking about things didn't get us terribly far. And that's why in the 16th and 17th century, people came up with something new, the scientific method. And ever since then, both our understanding of how the universe works and the applications we can derive from that have skyrocketed. At the beginning of the 21st century, when we are now, all of our lives are heavily impacted by the technologies that came from that, like combustion vehicles, computers, the internet, smartphones, all of that. And there's already been a lot of work done on the next generation of big technologies like quantum computing, self-driving cars, artificial intelligence, blockchain, you name it. You know, none of this would be thinkable without science. Interestingly, almost everybody agrees how important science is, but nobody really knows what it is. Nobody could really tell you a succinct definition. Most people just think that science is what the smart people in academia say, and so it's an opinion. What makes matters even worse is that even the vast majority of scientists have no formal training in what science is. So what exactly is science? How does science work? There have been, of course, a lot of attempts over the years to exactly codify the scientific method, and sometimes you get a 5-step program, and sometimes you get a 7-step program, and sometimes you get complicated diagrams with lots of items and arrows pointing there and back. And of course, there are some commonalities, but there are also differences. And again, the problem isn't that people are stupid, but that the world is complicated. These inconsistencies of sort have led some people, philosophers, to conclude that the entirety of science does not exist, or that the scientific method is a myth or a social construct, or come up with some absurd non-sentences like science is what scientists do. It means nothing. The point I'm trying to make is that in this case, when you're trying to be too detailed and too explicit, that whatever you come up with will only ever apply to particular fields, but not to others. And I think the way to go is to go down into the basic idea, to find the core of what science is. And what could this core of science be? We could say that science is a method for checking theories, and this check is performed by experiment. So if you're taking away just a single sentence from this entire video, this should be it, that science is a method for checking theories, and this check is done by experiment. To our modern sensibilities, testing things, testing ideas by just trying them out is so obvious that we wouldn't even call it a method or anything special. But it took us a really long time to come up with it and perfect it. And that's the entire central message of this video, that in science we don't use arguments or appeal to authority or appeal to a higher being or to logic, but only to what the experimental data shows. So there has been a lot of talk about science being a social construct or being irrational, or truth not being attainable in principle. And on the one hand, all of these ideas have given us new insights and new ways to look at things. But at the end of the day, all they are opinions, sometimes even hot takes. And on the other hand, cars do drive and planes do fly, and if I switch on my computer, it does work. So there is a very important distinction between an opinion and a fact. How does this basic idea we formulated of testing things in experiments square with actual real-life scientific research? I will mostly be talking about physics here because I am a physicist, but it applies broadly to most of the other sciences too. Generally, in physics you will find yourself to be in one of two situations. A, the experimental gap, where you have a theoretical prediction that has not yet been tested by an experiment because it hadn't been possible or practical. For example, there is a theoretical prediction of radiation emitted by a black hole called Hawking radiation. This has also not been tested in experiment or observation yet. And B, the theory gap, where you have experimental data that you cannot yet explain by a theory. For example, right now, as of 2022, we have no proper theoretical explanation for dark matter and dark energy. The experimental gap is pretty much what we've discussed, so testing ideas in an experiment, but the theory gap is somewhat different, and it begs the question how this fits into a definition, or a simple definition that we had. Scientists do not collect data exclusively for testing existing predictions of theories. Very often we simply collect data about things that we know very little about. The thing is that a theory that can explain the existing data can also make new predictions that can then be tested by further experiments or observations. So the end goal is always to have experiments decide which theories we reject and which we will use. So much for the basics. Let's do a deep dive into some of the details. Number one, hypothesis and theory. Technically, there is a very clear distinction that a hypothesis is a new idea that has not been tested yet, which you just came up with. And a hypothesis which has been successfully tested and proven becomes a theory. The thing with this distinction is, however, that it has not been very consistently adhered to. So in most practice that I'm aware of, especially in historical practice, there is a lot of different designations that are used. You have a law, or you have an axiom, or you have a postulate, and not necessarily a theory. It's more of those things that philosophers of science use, and not so much the scientists themselves, maybe. One thing though, there is one thing that really irks me, is when people go like, oh, quantum field theory is just a theory. If you do that, stop doing that. It does not mean what you think it means. 2, falsifiability and verifiability. First, you have to have an actual prediction which is testable. So once you do that, 2 things could happen. First up, you can falsify the prediction, meaning the outcome of the experiment does not agree with the prediction, or you can verify the prediction in the sense that the outcome of the experiment does support the prediction. Actually, that's falsifiability and verifiability is an entire can of worms in itself, and there will be a further video mostly about just that. For now, it's one important thing to say is that that the scientific theory can never be fully verified. So even if you have a lot of experiments which completely agree with the predictions of the theory, the only thing that really does is verify the theory for these particular situations and environments that you tested it in. And if you test it for some other configurations, then it might very well be falsified. For example, we've been using Newton's mechanics for 300 years, I think, until we found out that it will not work anymore. It will give wrong predictions when the speeds involved approach the speed of light, in which case you would have to use the special theory of relativity by Albert Einstein. And if a theory is falsified, you must either go back and adapt it or discard it entirely in the worst case scenario. So if it cannot be made to fit with experimental data, it has to go. There are theories that do not make clear predictions, that can pretty much explain away any type of outcome. And in one sense they can explain everything, but really they cannot explain anything in that case. So if your theory cannot be tested and cannot be falsified, it is not a scientific theory. For example, we've had psychoanalysis by Sigmund Freud, or Marxist history, or most postmodernist stuff. They can kind of fit any outcome into their explanatory frame, and so they don't make any predictions that can be falsified. When thinking about science, I'm always amazed, I'm always struck by two things. First, how simple the idea is, and yet how long it took us to come up with it. And two, how crazy it is that it works. That's because all of our scientific models are approximations and idealizations, and they are formulated with our very imperfect language. And even mathematics is an incomplete system, and we test it using apparatus and methods that are also error-prone and are also inaccurate. And still, in the end, it works. It gives results that work. So there is a quote by the great Danish physicist Niels Bohr, who originally said it about language, but it also fits perfectly to science in this respect. Anyway, it goes like this. Washing up is a miracle. We have dirty water, we have dirty dishcloth, and yet we manage to get the plates and glasses clean.